3D printing has become increasingly common in industry due to the ability to manufacture 3D printed parts quickly. As with any material, understanding its strength is essential to being able to build a design using the material. Infill of a 3D part is the pattern and percentage fill of the inside of the part. The expectation of this experiment is to find the most efficient infill pattern and infill amount for a cantilever beam in bending. Efficiency in this experiment is defined as the yield strength of the 3D printed part divided by the mass of the part. The experimental setup involves fixing one end of the 3D printed beam while the other end is attached to the LVDT. The LVDT is calibrated using a linear fit to correlate the output voltage of the LVDT with the deflection of the LVDT. This end is then loaded with weight, and the deflection is measured using the LVDT. This experiment involves concepts of error and uncertainty, sample statistics, uncertainty propagation, outliers, curve fitting, and calibration. The variables in this experiment are the dimensions of the cantilever beam, which are the length, width, and thickness of the beam, the applied force at the end of the beam, the vertical deflection at the end of the beam, the change in voltage of the LVDT, and the mass of the beam. The expected sources of error in this experiment come from the LVDT, the calipers, the mass of the beam, and the applied weight force, with the LVDT and the applied weight force showing precision error, and the calipers and the mass of the beam showing bias errors. The dimensions of the beam to be used during the experiment have not yet been determined, but the length will be between 10 and 15 centimeters, the width between 2 and 4 centimeters, and the thickness between 0.5 and 2 centimeters. The uncertainty of all of these measurements will be 0.005 millimeters, which is the uncertainty of the calipers that will be used to measure them. The precision error of the applied weight force is given by the weights used in this experiment, which is plus or minus 0.4% of the reported value. The mass that's applied will vary between 0 grams and 3 kilograms during this experiment. For the precision uncertainty of the LVDT, it's based on the standard deviation that is given. The LVDT reports values between 10 volts and negative 10 volts, and the standard deviation is about 0.01 volts. The bias uncertainty of the mass of the beam is given by the scale that it's measured by, which is plus or minus 0.005 grams. The mass of the beam will vary, depending on how much infill is given, between 15 grams and 150 grams during this experiment. The following video shows a single run-through of the experimental setup. The beam used has a square grid infill pattern at 15% infill. No personal protective equipment is needed for this experiment.
There's the beam right there. There's the setup with it all picked up. And then as a flex, this is continuous.
That was hit the target. Yeah.
Let's see.
I feel like it should be faster. That one, it wasn't pushed all the way down. It needs to.
Alright, so that's explaining that. We can talk about how it's continuous. And then should we show how it would change when we do it as like a high speed?
Yeah.
Oh, I see. We technically want to be accurate. I'm just capping the pressure here.
So then Jake, maybe throw like some weight on there.
Or like point.
What's the skateboard ramp? There we go.
Okay, and then we would measure the standard deviation and the voltage average.
Plug that baby in to our Excel, which we've already started. Define our calibration fit, and then we can apply forces and our deflection calculations from that.
The modulus of elasticity for this beam at room temperature was found to be about 1.59 gigapascals. Many steps were taken to minimize error in this experiment. The 3D printed part was designed to minimize error with a notch for the LVDT to sit in to avoid slipping, a hook to ensure the load is placed in the same spot every time, and an extension to make sure each beam is fixed at the same point. Other steps taken to minimize error in this experiment include testing each instrument to ensure they work properly, the calibration of the LVDT, and ensuring each instrument is stable while in use. The main gap to be addressed is the loading mechanism. The load was originally planned to be hung underneath the beam, but there was not enough room for the load. The design will be changed to allow both the load and the LVDT to be placed at the top of the beam. The main other change is shortening the width and the thickness of the beam to allow yield at less weight.